Hi, thanks for your interest. Today we are presenting SpaceTools, a framework that teaches vision language models to use specialized perception tools for spatial reasoning via double interactive RL. We are building the future of robotic agents that do useful tasks for you in the real world. The challenge is that today's agentic systems struggle with the spatial reasoning robotics demands: precise geometry, 3D grounding, depth, pose. Different tasks need different 3D perception, and that creates two key challenges. First, acquiring skills. The model needs diverse specialized perception capabilities. Second, adaptive use. It has to pick the right tool for the task and recover when tools fail. Our answer is tool-augmented spatial reasoning, training VLMs to use perception and robot control tools on demand, via interactive RL. The figure on the right shows what this unlocks. Only the tool calling agent answers which pedal is smallest, and where do I press it, correctly. Our method is double interactive RL, DIRL. Two phases. First, we teach the model by SFTANG on two trace sources, 2K traces from a single tool specialist trained with interactive RL, plus 6K multi-tool traces distilled from Claude. This prevents the model from collapsing during exploration. Second, we resume RL with the full toolset using GRPO and live tools in the loop, and that's where the model learns to coordinate tools and recover from failures. DIRL's exploration phase needs the model to actually interact with tools, calling segmentation, depth, pose, and grasp models during rollouts, getting back real predictions, and conditioning its next action on the result. That live interaction is what Toolshed enables. It hosts each tool in its own isolated environment, lets many rollouts hit shared tools concurrently, and fully decouples tool execution from the policy loop. Without Toolshed, interactive multi-tool RL simply isn't tractable. That's why the framework and the infrastructure are co-designed. Here it is in action. Watching this clip, SpaceTools first segments the scene, calls depth and pose tools to localize the object, plans a grasp, and recovers gracefully when a perception tool misses. The whole loop, perception, action, recovery, runs end-to-end with the policy in charge. Here's the full benchmark table, 10 metrics across 4 model families. SpaceTools 3B is best, bold green, on 7 of 10 columns, and second best, underline, on 2 more. Look at the BOP Ask Pose column. Every frontier model scores near 0, Claude 1.7%, GPT 5.9%, Gemini 0%, and we get 34%. Same story on Grasp Mace and Grasp SR. The tool-free fine-tuning rows show that vanilla SFT/RL on the same base model loses 12-16 points versus DIRL. On real-world manipulation, SpaceTools matches or beats Claude 4.5, a much larger frontier model, while responding 3 to 4 times faster. Pi 0.5 and Zero-Shot Quen fail outright. The strip at the bottom shows a single task end-to-end. SpaceTools picks the flashlight and places it in the transparent bin, with the per-step tool calls and reasoning visible. The learned policy picks the right tool for the job, pointing for relations, depth for distance, multi-step composition for pose, and, crucially, it learns to recover when a tool returns an obviously bad answer. These behaviors are learned via DIRL. Both the teacher traces and the interactive RL phase shape them. 3 contributions: DIRL, the training framework; Toolshed, the infrastructure that makes it scalable; and SpaceTools 3B, the model that ties it together. The bigger picture, interactive RL with live tools, is now practical at scale. Imagine a future where adding a new perception or control capability to a VLM is as simple as plugging in a new tool, no retraining with huge data, no new architecture. That's one possible path toward general-purpose embodied agents, and we hope this work opens that door. Thanks for watching. Everything's on spacetools.github.io. For questions, please reach out to Seachin, Valtz Blookies, or Jonathan Tremblay, or come find us at the CVPR poster session in Denver.